So here we go. So question, what does a vector field have to do with rate of change? What does a vector field have to do with rate of change? What's the connection between a vector field and rate of change? Anybody? What do you think? So, you can answer as I walk around.
As it gives you a change in x and y in relation to p. So as the gives you a change in x and y.
Okay, maybe. So in terms of concepts we've talked about. Okay, good. So so the vectors might show us rate of change if what? What? If it's a gradient field, right? Good. So if the vector field is a gradient field, then that vector field is showing us the rate of change of a multivariable function, right? Like a surface. It's showing us direction and magnitude of greatest rate of change for some surface, right? Some multivariable function. Okay, so let's turn the tables. What's the rate of change of a vector field? So far we've seen vector fields could be describing the rate of change of a multivariable function if it's a gradient field. But what about the rate of change of a vector field as a function itself, right? Rates of change, or vector fields are functions. Functions have rate of change. So what about the rate of change of a vector field? Yeah? Okay, yes, all right. So you're relating it back to the, yeah, possibly, yep. If it's a gradient field. Okay, so this is the topic for today. And actually, in vector fields, there are two, because now we're in multi-dimensions, there are like two totally separate and different kinds of rates of change for a vector field. Okay? The first kind of rate of change is called curl. Okay? Curl is rotational rate of change of f being, f is our vector field. So rotational rate of change, and this relates to what we talked about last time. So what we're going to do is we're going to investigate a small element of a region in a vector field. And our vector field is PQ, right? So I'm in a two-dimensional vector field, PQ. I'm going to focus on that little yellow rectangle. We call that dA. It's a little chunk of a region. So let's blow that up. And so dA is comprised of a change in x and a change in y. And it's in the vector field. So it's really small, but there may be a variation in the vector field as you move across it, right? So as you move that little dy, you make it a change from the force of the vector at the bottom to the top. So B is bottom, T is top. And then there might be a slight variation in your vector as you go across. So I'm showing F left and F right. So this is kind of like, what's the vector field at this very small element in our region? And there may be variation, right, as we change a little bit in x and a little bit in y. Okay, so according to the right-hand rule, counterclockwise rotation is positive, right? According to the right-hand rule, counterclockwise rotation is positive, and so we're going to say the curl is 0. The rotational rate of change curl is greater than 0 for counterclockwise rotation. Counterclockwise rotation. Okay, so I'm going to look at the components of these, right? So purple for P, right? Purple for P, and then really light green. Can you see the green vectors? The vertical components, those are the Q components, right? So the x components of all these vectors in the vector field are P, so purple, P, and green for Q, right? Green for Q. It's the closest thing to G I could find. The closest thing to Q I could find was a G, so green, right? Okay. So the question is, I want to just focus on the vectors above and below. I want to focus on the vectors above and below. Which components are going to contribute to rotational or rotation rate of change? Which components? The horizontal components or the vertical components? So the P's or the Q's? If I'm looking at the top and the bottom vectors, what's going to contribute to rotation around this little element? The P's or the Q's? Some people are saying P's. Agree with that? So what's going to cause twisting, right? What's going to cause rotation? The purple or the green vectors? If I'm just looking at these two, the top and bottom. Yeah? Right, so do you see that it should be the piece, right? So when it comes to rotational rate of change, and we're looking at the vectors above and below, the Q's don't matter. Those green vectors don't matter, okay? So, oh, it's too bad. They're not darker. But this one you'll see. There we go. Bye. Okay, so when we talk about rotation, all we care for the top and bottom vectors are the P vectors. Okay? So we're talking about rate of change. So remember our rate of change. So given a change in y, this is, remember back when we kind of redefined rate of change in this class? We said, given a change in y, the change of p is equal to something times the change in y, right? And that was the rate of change. So what rate of change is that? That's going to give me my change in p, how much these purple vectors change for a change in y. What rate of change will that be? Which rate of change would be? So to get the change in P for a change in Y, the rate of change will be? It's just going to be maybe? The partial of P with respect to Y, right? The partial of P with respect to Y is going to be how much P changes for a change in Y. And that's going to be part of what contributes to rotation around this little element. Okay, likewise. So now question, what components of the vectors right and left of D and A cause rotation? So the P's or the Q's. So now I'm talking about the left vector and the right vector. Which components are going to contribute to rotation from those two vectors? The P's or the Q's? Q's, the verticals, right? The vertical is going to cause rotation. The P's won't, right? The P's won't. So let's get rid of those P's. There we go. Okay. So we still got the green ones there. And so what's our rate of change of how much Q changes, right? How much that green vector changes for a change in X? What's that rate of change? Partial of Q with respect to X. So both of these, the partial of P with respect to Y and the partial of Q with respect to X, are contributing to rotation around this point. But remember we said, what? We said that, shoot, not my pen. We said that positive rotation is, I need my pen. Okay. So we said positive rotation is counterclockwise, right? So let's look at the Q's first. So as X increases, I'm showing, I'll make it a little darker here. Does that show up better? There we go. So as X increases, if Q increases, that's what I'm showing, right? I'm showing an increase in Q for an increase in X. Does that result in clockwise or counterclockwise rotation? If I got more upward force on this side than I do over here, is that going to turn it clockwise or counterclockwise? Counterclockwise. So for an increase in X, if I have an increase in Q, a positive dq dx gives me counterclockwise rotation. So that matches up, right? Now what about dp? dy. So for an increase of y, if I have an increase in p, does that contribute to clockwise or counterclockwise rotation? Clockwise. All right. So with p, it's the opposite effect. So if we want positive curl to be counterclockwise, then we got to we want the positive contribution from partial of q with respect to x, and we want to take the opposite of the partial of p with respect to y to sum up all of the counterclockwise rotation and get the counterclockwise rate of change, right? Rate of change. So qx minus py should look familiar. Or have we seen that before? Green's theorem, right? So what is this? This is rotational rate of change. So when we were doing Green's theorem, we were doing the accumulation of all the bits of change by looking at the rotational rate of change, right? By taking accumulation of circulation by taking the rotational rate of change times a little bit of area and adding that up. And that gave us the total circulation, right? So this is what we call the curl of F. The curl of F is the rotational rate of change. But curl is a vector. So what would its direction be? So for counterclockwise rotation, what would the direction of the curl be? It's a vector, has a single direction. So remember the right-hand rule, right? Counterclockwise rotation, according to the right-hand rule, gives us, what direction would that be? Out of the board, right? So the vector is going to be orthogonal to the plane of rotation, right? It's rotating in the plane of the screen. The curl is going to point orthogonal to that plane of rotation. So according to the right-hand rule, it's going to be in the positive k direction, coming out at you. So the magnitude is the strength of rotation in that plane, and the direction is the vector orthogonal to that plane. So that's that would be two-dimensional curl.
And so if it's coming at us, or in this scenario, that means the curl is positive.
Right, if it's in the positive z direction, right? So positive k, that's positive curl. So it'll be counterclockwise rotation in the xy plane. Make sense? Okay, but we have curl in R3, so that was kind of R2. So in R3, basically, what we've got in R3 is we've got three different components of that, right? So I just showed you one component by showing you the R2 version of curl. I showed you one component of three components of curl in R3. So you imagine now like a does it show up? So it's really light. So that show up? A little better. So now imagine a little like three-dimensional element in space that has three different ways it could rotate all simultaneously, right? So that will all create one plane of rotation, right? So you could have a rotation in xy, you could have a rotation in yz, a rotation in xz, and put all those together, and that thing is rotating in a certain plane, right? That thing's rotating in a certain plane. So let's just walk through quickly. We'll walk through now. This is looking at the an element in the yz plane. And so now I've got my Q's are my green ones here. Horizontal components are still, all right. So Q are your Y components of the vectors. Now they're horizontal in the YZ plane, right? And then P, Q, and I think the red ones are showing up. So then our vector field is now three-dimensional. And what's our convention? So P is the x component, Q is the y component, R is the z component of the vector field. Three-dimensional vector field, right? For every point in space, we have a vector. It has a x component, a y component, and a z component, which we'll call P, Q, and R. So when I'm looking at the rotation in the YZ plane, I'm looking at the horizontal components are my Q's, Y. My vertical components of those vectors are the R's, the red ones. Okay, so when I talk about change in Z, so when I look at my change in Z, what's going to contribute to rotation for change in Z? My Q's or my R's? My Q components or my R components? What's going to contribute to rotation when I'm talking about change in Z? I didn't think that was a hard question. Q, right? The horizontal components of these top and bottom vectors for change in Z are going to contribute to rotation. So that's going to be what? dq, the partial of Q with respect to Z. And then for a change in Y, which components are going to contribute to rotation due to a change in Y or horizontally? What's that? So the green or the red are going to contribute to rotation for a change in Y. Green ones or the red components? Red, right? The red components, so for change in Y, horizontal change, it's the red components that are going to cause this thing to twist, not the green ones. So that's for a change in Y. I'm looking at the how R changes, right? Those are my Z components of the vectors. So what will in this plane then, what contribution to the curl will we get for the YZ rotation? What will it be? Can you write it down? So I'm talking about in the YZ plane, or the YZ parallel to the YZ plane, what will be my contribution to the curl? What will it be? Anyone know? Okay, so he wants RY. That will be positive because for a positive Y we get positive, and a positive R we get counterclockwise. Minus QZ, right? Because for a positive Z, a positive Q makes it turn the other way. And then in the I direction, right? Very good. Maybe. So the x-axis rotational rate parallel to YZ is going to be RY, partial of R with respect to Y, minus the partial of Q with respect to Z. And that will point in the, right? So counterclockwise in the YZ plane means, by the right-hand rule, positive x direction. And so then likewise you have the third, so I showed you the first one for R2. And there's going to have to be that contribution to the curl. You're going to have this contribution to the curl for a rotation, parallel to the YZ plane. And then you're going to have one more. We won't go with it. It'll be just the same thing again. But I'm going to show you an algorithm for calculating the curl, kind of algebraically. Any questions on this? That's kind of the backdrop here, the concept behind where curl comes from. So it's just looking at whatever components of the vectors in the vector field contribute to rotation, right? So in the horizontal direction here, only those vertical components, which would be the R vectors, are going to contribute to rotation in this plane, etc. So we have this thing, what is that? Do you remember what that is? It's the gradient, right? So this gradient is actually, it doesn't only, so we've seen it operate on what, a multivariable function. So we saw it, we took the gradient of f. Well, this gradient can operate on vector fields as well. So notice that we wanted, let's go back a screen here. Notice when we were changing in the horizontal direction, which components did we want? We wanted the vertical components, right? And we were changing in the vertical direction, we wanted the horizontal components in terms of tabulating up twist, right? Tabulating up rotational rate of change. So what operation is that? So we want what? We want this product in as much as they're what? Orthogonal, right? So for dy, we want the vertical components. For dz, we wanted the horizontal components. So this is really about orthogonality, right? We really wanted to get rotational rate of change. It's all about taking the orthogonal component of those vectors to the whatever change we're talking about, dy or dz or dx. So that's why what we do to get curl is we'll do a cross product, right? Cross product of the gradient operating on the vector field. And so we're gonna set up the cross product algorithm with I, j, and k as the first row. And then this is what we call the gradient operator. So the gradient is partial with respect to x, partial with respect to y, partial with respect to z as the second row. And then our components of the vector field, p, q, and r, as the third row. And we're going to follow the cross product algorithm, which was finding the determinant of this matrix. So it's kind of like determinant, but it's not really, because we're not really multiplying. We're doing the same algorithm, but it's like we're taking the derivative of r with respect to y, and then that's going to be times I. So it's not multiplication per se, but it's going to follow the same algorithm. So how did we do this? Remember we said ijk and then ij, and so you rewrite the first two columns, pq. And then what do we do? Right, we went down to the right. And then we went there's 3 diagonals down to the right and 3 diagonals down to the left. And then when we went down to the right on those 3, we added all those, and then we subtracted all the ones coming back to the left. So what will it be? So we have the partial of r with be ry, what? Minus qz. Is that the one we just found? And plus the j direction, what? P with respect to z, what? Minus r with respect to x. So that's going to be that's the one that we didn't show. That's going to be the contribution, what? Parallel to xz plane in the direction of positive y. And then the last one we showed was, that was the first one we showed, was for z. It's going to be what? Q with respect to x minus p with respect to y. That's coming back the other way, this way. Or is it here? Okay. So now this is all the contributions in R3, all the contributions of the vector field to rotation, right? To rotation, kind of broken down by parallel planes in the x, parallel to the xy plane, yz plane, xz plane. But when you add them all together, you get a particular rotation, right? Could be like diagonal, right? You get a particular rotation that has a plane. All right, so then the magnitude of this is The magnitude of the curl is the strength of rotation in that plane, and the direction of the vector is orthogonal to that plane of rotation according to the right-hand rule. So that's the curl. And so rather than memorize or try to follow this formula, what I do is I just always go back and set up the matrix. Like when I have a particular vector field that I want the curl of, when I know what P and Q and R is, I just set up the matrix and I work it out. I don't try to memorize and plug into that formula. I think it's just easier just every time, set up the 3x3 matrix, follow the determinant of the matrix algorithm, and then crank out your curl, right? So again, the magnitude of the curl is the rotational rate of change in some plane. The direction of curl is according to the right-hand rule. It's a vector orthogonal to that plane of rotation. Now here's a huge key point. Curl is a function. Okay, what does that mean? Rotational rate, it's a point-wise phenomenon. What does that mean? It means it varies dependent on your location in the field. So curl is a function where you pick a point in the field. The curl tells you what the rotational rate of change and direction is at that point. So it's another vector field, right? So you're getting the curl is another vector. So the curl is as a whole vector field, right? So curl is like you start with a vector field and you get another vector field, right? So F is a vector field, and then the curl of F is another vector field. So given a point in space, you've got a vector in your vector field, and you've got another vector at that point that represents the curl of F. Again, how much strength of rotation in a certain plane, and direction tells you what that plane is, right, by being orthogonal to it. Okay, any questions on the setup here? So let's look at some examples. Okay, here's a vector field. So question, is a curl positive? I have it right here. Is the curl positive, negative, or zero? What do you think? Is the curl positive, negative, or zero? Positive. Why positive? Because it's counterclockwise, right? Okay, well let's take a look at that a little more in depth here. Investigate that. So let's just pick a point here. I'll pick a point right here. And let's kind of look at, so let's look at horizontal components of vectors here. One. So what are those vectors doing as we go north there? As we go in the positive y direction, what are those horizontal components doing? They're getting shorter or less short to the left, right? More or less negative as we go north. I mean less negative, right? What kind of rotation would that indicate? Clockwise or counterclockwise rotation? See that would indicate clockwise rotation. This is stronger down here than this is up here. So it's kind of in terms of in the y direction, changing in the y direction, those horizontal components are kind of indicating clockwise rotation. Let's take a look at x. Where was I here? What about these? Going this way. How about these vertical components if I'm going to the right? Indicating clockwise or counterclockwise rotation? This vector is longer than this one, which is longer than this one, indicating clockwise rotation. I thought you told me this vector field had positive curl. What was wrong with that conclusion? Besides the fact that it was wrong. Why was it wrong? Yeah.
We were looking at the curl field,
Yeah, okay, that's kind of the right idea. Yeah.
So curl direction will always appear on my vector field.
Right, what did I just, so what did you say?
we had to look at the change.
Right, so what did I say right before we did this exercise? What did I say? Curl is? What's that? It's pointwise. It's a pointwise phenomenon, right? It's a pointwise phenomenon. It's not a global phenomenon, okay? So yes, globally, this thing rotates counterclockwise, right? But locally, at any given, at least at this point, based on our analysis by visualization, the actual rotation is clockwise. So a good thing to think about is like a little flywheel, right? So if I put a flywheel in here, you know what a flywheel is? It floats. It's like if this is like a flow field. I imagine this is like a whirlpool. I'm going to put a little paddle wheel in here that's free to spin and free to move. It's just totally free to according to what the currents are doing, right? So what's that? How is that going to move? How's it going to move?
It's gonna go left to spin, right?
Yeah, right. So it's gonna move around in a counterclockwise direction, but that's not what curl is. What does curl have to do with? How that thing spins on its axis. And so as it's moving around counterclockwise, this thing is going to spin clockwise. And that's what the curl is, right? It's pointwise phenomenon of rotational rate of change. So you can imagine that, right? You can imagine as it moves around, it's turning, it's turning clockwise as it moves around counterclockwise. Right? That makes perfect sense. All right, so just underscoring the point that curl is a pointwise phenomenon, not a global phenomenon of the field. Okay, let's look at this one. So what about this? So here's a vector field, kind of shows the same kind of global counterclockwise rotation. So what's the curl? What's the curl? Positive, negative? What's the right answer? We don't know, right? So the answer is just by looking at the thing that is a whirlpool that's turning counterclockwise, we don't know. So let's go ahead and do the math. So here's this vector field. It is negative y over x squared, 1 over x, and 0. So I want you to use the algorithm for curl to find out what the curl is, right? So this is a negative y, x to the minus 2, x to the minus 1, and 0. That's f. So I want you to find curl of f by set up the matrix, right? IJK, the gradient operator, the partial derivative operators, and then you put your PQ and R, and then you work out the determinant and see what vector field you get. Okay, and I'm going to take attendance. How do you do that? Write it down. I got to take it off the screen. So I'm going to mute the screen here for a sec. Make sure you got that down, and you're calculating the curl of f to see what it is. What'd you get? Did you get 0 for everything? You should have got 0, 0, 0. So what does that mean? What does that mean about this vector field? Think about the flywheel, right? The flywheel's moving around here. It's going to move around counterclockwise. So what's going to happen? It's not going to rotate. So a curl of 0 means irrotational vector field. There's no rotation point-wise. The whole thing could be spinning as globally, but at any given point, there's no tendency of rotation, right? The rotational rate of change is 0. Okay, and what is our z component again? What's the z component of the curl? I know, but what is it? Q. What is it? And what did we talk about this last time? What does that mean when that is 0? Right? That was in a Green's theorem. Remember when everything canceled out or everything fell to 0 in Green's theorem? This was in what kind of field? Conservative, right? Irrotational vector fields are conservative. Or conservative vector fields are irrotational, we should say, right? But they're one and the same, right? So if you have a conservative vector field, that means it's irrotational everywhere. And your curl is 0, or your qx minus py is qx equals py, and so then that rotational rate of change is 0. Okay, question on curl. Questions on curl. So there's a whole separate type of rate of change for vector fields. We can start that, and we might even finish. It's a lot easier. Any questions on curl? Yes, please. No. So that was just an example of just tying it back to what we turned before. But in order for it to be irrotational, all 3 components have to be 0. If there's one non-zero component, it's not irrotational and it's not conservative.
So you shouldn't normally get constants for this because it is a function, right? Like normally you would get.
No, you can have constant function, right? So just like with functions, you can have a constant function. You could have constants. These could be functions of x, y, and z, or they could just be constants.
That just mean everywhere is the same.
Exactly, right? So if your curl was 1, 2, 3, then you have that would define a constant rotational rate of change at every point. Yeah, that's perfectly legitimate. Other questions? Okay, so let's talk about the other kind of rotational rate of change, or no, other kind of rate of change of a vector field, which is called divergence. Divergence is rate of change that's dealing with expansion or contraction at every point. So this is a lot easier. So we're going to do the same thing. We're going to blow up our little element. We're going to take the P and Q components, and we're going to say for a change in Y, or maybe I do X first, I don't know. Yeah, so for a change in Y, what's going to contribute to expansion or contraction? The P horizontal components or the Q vertical components? What's going to contribute to, if it's compressing or expanding? Q's, right? So the P's, we don't care about that. We're going to go away, right? And then for a change in X, what's going to, for a horizontal change in X, it's going to be the P components, right? The horizontal components. So now what are we talking about? We're talking about in the direction, we want the parts of these vectors in the direction of that we have change, right? So in the direction of X, we care about P, and in the direction, so we want that, and in the direction of Y, we care about Q. Parallel, right? Parallel. So the total rate of expansion is just going to be, we're just going to sum it up. We're going to sum up the effect of expansion in the Y direction from the Q components, and the expansion or contraction contribution in the X direction from the P components. So we're just going to add them up. And then in 3D, we'll just add up all 3. So what is this a matter of? This is a matter of what? Dot, right? Dot, because it's in the direction of, so if we have a change in x, we want the part of the vectors in the direction of the change in x. And if we have a change in y, we want the component of the vector in the direction of y. It's going to be dot product then. And this is the divergence. Now divergence does not have a direction. It's a scalar function. It's just going to, you're just going to get a number. You don't get, there's no direction to it. It's just how much expansion, positive, or contraction, negative. And then so it's going to be the dot product of this gradient vector, right? So we take the gradient operator vector, partial of x, partial of y, partial of z. And if we do the dot product with our vector field p, q, and r, what does that mean? It means take the partial of x, p with respect to x, take the partial of q with respect to y, take the partial of r with respect to z, and add them up. And again, so that whereas curl was a vector function, it had magnitude and direction, right? The direction orthogonal to the plane of rotation. Divergence is just a scalar function. It's just how much, right, expansion or contraction at any given point. So this is much easier. You just add the corresponding partial derivatives for each direction. You just add them together. Let's go back to that last example we looked at here. This one that you found the curl, it was irrotational, right? So if you look at this one, we'll start this example next time, and I'll do this other thing. Let's look at this. This one. Okay, so right there is this vector field, which is x over x squared plus y squared, y over x squared plus y squared. So now I'm showing you that in this picture right here. So expansion is positive divergence, contraction is negative divergence. Is the divergence here positive, negative, zero? What do you think? Positive. Why positive? Because it's moving outward, right? Big as I can here. So look, take this component here, and this component. What are these vectors doing as I move to the right? Getting smaller. So as we move this way, the actual is getting smaller. What does that indicate? Negative or positive? Negative. Same thing going up. As we move up, vectors are getting shorter. So I think actually this is actually zero divergence in this one. If we were to do it. Can we do it fast? Do it fast. So partial of So here's my vector field. So the partial of the first with respect to x. Quick quotient rule here. Ready? Low d high. So low times 1 minus high d low over low squared. Plus, so that's the partial of p with respect to x. Low d high. It's going to be with respect to y. So it's going to be low high minus high d low over low squared. Do the math. Well, I got x squared plus y squared minus 2x squared What's that? Is that y squared minus x squared? What's this? X squared plus y squared minus 2y squared. Is that x squared minus y squared? Common denominator? Add the numerators? 0. So this is actually, this field is, it looked like it was negative divergent, but it's actually 0 divergence. It's called incompressible.
So why does it look like it's negative divergence?
Just the way the rendering is. So actually, all those components should be equal, right? So if all those components are equal and all those components are equal, then it's the divergence is 0. So an incompressible vector field is when the divergence is 0, neither positive nor negative, but that does not relate to being a gradient field or being conservative. That's the curl, right? So when the curl is 0, it's irrotational. That's when you have a gradient field or a conservative vector field. Incompressible is a different conversation, okay? It just means, all it means is divergence is 0. There's no tendency of expansion or contraction anywhere in the field. Yeah, Max?
How does the direction of the vectors contribute to the divergence?
So you think about what would happen if you traveled in that direction. Does that make sense? So I would say if we went to the right and those vectors got smaller, it would be negative divergence. And if we went to the right and those vectors got longer as we moved to the right, it'd be positive divergence. It'd be expansion.
So if, like, in the example where these are not equal vectors, like it is getting smaller,
Yeah.
But if you had the vectors pointing in opposite directions, like those were just like flipped around and they're all going inward, would the divergence go from negative to positive, or would it change?
It's pointwise, so you just have to look pointwise. Move in the direction of the field. If your vectors are getting smaller as you move in the direction of the field along with the vectors, you have negative divergence. As you move along whatever direction you're going that the field takes you, if the vectors get longer, then that's positive divergence. Okay. Have a great weekend. So remember, you got written homework due Monday based on the video that I posted. Look on Blackboard.